Videos and upload it. Will you be getting it?
Yeah, sure. Couldn't do that this week. I'll collect all these videos and put it on the web, and you will get notifications to download and view it. Yes. Sorry about that. Small lapse from my side. So what I was telling is that I really want to keep the integrity of what we do here because we are going in steps. And if we don't have all these things that we learn up to whatever point, right? If you don't have the integrity of the contents, at some point of time you will lose your GPS. You don't know where you are, what you're doing, what is in the past, what is coming up. So then you will be in all sorts of trouble. So that is why I always give this little summary before we get going. So when you see a block diagram like what you see over here, if you see this big rectangle, right? It is a system. It can be a machine, it can be a motor, it can be a sensor-based system, it can be a robot, can be a vehicle, whatever it is. So when you write down the basic equations, right, for the system, you get this block diagram, right? In fact, you get this equation, transfer function, which is how the input is related to the output, right? Now, if you want to use this device and make it a feedback control loop, what you do is you take the output here, YS, and you connect it back to the input, not directly as input, but you compare it with a reference. Now, when you think about controls, you think about a reference, right? So reference is the desired response, actually, right? When you set your air conditioner setting 27, 26, 24, it is this RS, input. And then the compressor and other actuators in the air conditioner will try to make the output equal to the input. So that is how the feedback loop runs. So after about a minute or two, probably you get your YS equal to RS, right? Sooner the better. Now, when you do all these things, right, you have to do some sort of design, right? So how to get from where it is right now, let's say the present value of the output and final value of the output. Final value is basically RS. So how to get it from present value to the desired value in a peaceful manner and also a bit faster without taking too long, right? And also without going up and down oscillations, right? You want to efficiently reach the endpoint. So this the efficiency and smoothness, peacefulness of changing the state from present to the desired is entirely the objective of designing a control system. Sometimes we prefer shortest time. Quickly we want to get to the desired value. Sometimes we want to go slowly, right? Following certain criterion. Sometimes we allow some oscillations to happen. So whatever the requirement may be, we can't say it's always like this. It is changing. It depends on the requirement. Then we design according to that requirement. So when we design feedback controls, now if you can see it over here, what we are really trying to do is to find out this value, K, feedback gain. So eventually, the whole thing of designing a control system is, for most parts, designing the feedback gain, K. Understand? For different values of K, you get different responses. And one of those responses would be exactly what you are looking for. Whether it is fastest time, smooth profile from present to the desired value. So whatever it is, you achieve it for a certain value of K. So to find what the value for K is basically the design criteria. So one of the design criterions is very classical criterion is root locus design. Okay, so this is how things are connected to each other. So, so the other thing I want to tell you right here is that this is not the only uh, the feedback design criterion. There are many other design criteria as well. Okay. So now this example is draw the root locus of the following feedback control system. Right now you know what it is. Right, what you are supposed to do. You are supposed to draw the root locus of uh, the feedback loop here. And we also know that this is the open loop plant, open loop transfer function. And when you have the closed loop, it is 1 plus k GSHS, right? HS is 1. So therefore, it is 1 plus k GS. This is GS is equal to 0. So this is the this is in fact not the closed loop transfer function. This is the root locus criterion. So I will adjust it later. This is the root locus criterion. Okay. Now, now let me ask: has any one of you tried this at home? If so, please let me know. This example. Has anybody tried this home, and has anybody been able to sketch the root locus of this one? No one? Okay, right. Anyway, I didn't ask. I was just curious to know. So, when you ask, okay, design, okay, draw the root locus of a certain plant, right? When you break it down, the meaning of that question is the following. Number one, asymptotes and asymptote angles, angle of departure, breakaway point, if there's any, right? Maximum stable gain, right? As you know, for some gains, the system could be unstable. So if there's any gain and if there's any situation where our system can become unstable because of this gain, you have to find that out. And also number 5, there's something else, forward gain for unity DC gain when k equals 30. So that is something else. After you design your plant, let's say k equals 30, and you are asked to design or calculate for forward gain to maintain unity DC gain. So unity DC gain means when you say R is whatever value, you get the same value over here, 1 to 1. Okay. Right. If you are able to work this out, number 1 to number 5, you are done. You're done. Right. So when you study also, you have to figure out the individual components. I want to study this, like that. It's a finite number of items. Okay. There's a boundary. So if you can understand all these individual chunks, you are done. So it's pretty specific. So let's, and by the way, before this 1, 2, 3, 4, 5, they start after some basic stuff. That is what you need to understand what the open loop plant is. For example, here, this is the open loop plant. And also, if you remember what I said last time, the closed loop plant is a bit complicated. Okay. But the closed loop plant's behavior can be understood by looking at the open loop transfer function. That is a very serious advantage in the root locus design. Open loop transfer function is fairly simple. Just this. So you will understand, you will see here that when we try to sketch the root locus, right, we almost always do it considering only this part, the open loop transfer function. Okay, fine. The other thing I want to tell you is that if you get a plant, right, you have the plant's poles and zeros. For example, this plant, there are poles and zeros. Poles are over here, zeros are over here. Okay, poles and zeros. Now, if you connect a loop and make it a closed loop system, what are the poles? So now poles don't have specific values. Poles are changing as you change k. Poles are moving. But there's a start point. Start point is here. If you look at the open loop transfer function, the poles here are the start points, start or initial locations of the poles when there's no k, when there's no feedback. I think we saw that last time, right? Now, when you have some non-zero k, poles are now at different points. When you change k, poles move. So then you see if there are, let's say, 5-6 poles, right? It's like 5-6 pieces in the air. They are moving like an air show. Different aircrafts are moving at different directions, just like that. As you increase k, the poles move. And when you increase k to infinity, some of these poles will go to the zeros here, open loop zeros. Okay. So if you have open loop poles, say 5 of them, and open loop zeros, 3 of them, right? 5 of these open loop poles, right, after traveling through the root locus, end up being at the zeros when k equals infinity. Okay. So other poles, n minus m, remaining poles will go to infinity. So this is the start as well as the end of the poles. They're all here in the open loop transfer function. Start as well as the end, right, of the poles. In between, we don't know. We have to calculate, figure out. Then that is what is called the root locus. Fine. So having said all of these things, now you are in a better position to get going with the root locus design. First thing is to figure out what are the start points and end points for the poles of the plant. Okay. Right. So for that, what we do is so let's take k equals 0, which is open loop transfer function characteristic equation, right? So I think you have to work with me here, right? So this is the characteristic equation. S times s plus 3 times s square plus 6s plus 20 equals 0, right? You have to write it down, work with me, right? This is the first manual example. So if you work with me, you will understand it perfectly. So when you set it to 0, you can calculate the solutions here. S equals 0 is one solution. S equals minus 3 is another one. And then this part is a quadratic equation. You can calculate the solutions as minus 6 over 2, that is minus 3, plus or minus square root 6 square minus 2 times 20, right? That is divided by 2, right? So eventually, when you work it out, you will see it's root 11, right? Check that out, right? So, so these are the open loop poles of the plant. Open loop poles of the plant. right? So one of the start points is 0 right over here. The other one is at -3 over here. All these crosses are actually poles for k equals 0. And the other two poles are actually conjugate pair, -3 plus or minus j root 11. Right? So here and here. So this is the first thing you do. Now you say there are 4 poles, right? 2 over here and 2 over here. So 4 poles and m equals 0. No zeros. So of course there are no zeros here, right? Numerator, if there is a polynomial here, you have to set it to 0 and calculate the solutions. But here it is just 1. So therefore no zeros. Right? So you are in a situation like this where there are no zeros but 4 poles, which means all these poles will have to go to infinity. Will have to go to infinity as you increase k. All right. So that is the first step. That is the first step to understand, figure out the start points for the poles and the end points for the poles. So now we have done that. Start points for the poles are like this. End points are at infinity, but we don't know where they are. We only know they are at infinity. Now let's take one by one the root locus rules. What about asymptotes? Asymptotes. So remember the equation for asymptotes. I just pedaling back for asymptotes. Where's that? Here, asymptote angles. This is the equation. I gave it without a proof, right? If you want a proof, you can read Agatha's book, Franklin, Lewis, any of these standard books, right? 180 degrees plus 360 times L minus 1 over N minus M. So that is the equation. N is number of poles, M is number of zeros in the open loop plant. L goes from 0 to 1 to 2 up to N minus M minus 1. Okay. So we'll use that equation because as you know, all of these 4 poles, they are actually going to infinity as you increase k. So they are actually going through 4 straight lines. We are now going to find out the angles of these 4 straight lines. Okay, they are called asymptotes. So the first one is like this: 180 plus 360 times 0 minus 1 divided by n minus m, which is 4 minus 0. The answer is minus 45. So this is minus 45 line. The second one is 180 plus 360, 1 minus 1 divided by 4. So that is plus 45. That is plus 45 line. Third one is 180 plus 360 times 2 minus 1 over 4, 135. The fourth one is like this, 225. So you have 135 and 225 like this. So eventually you will see this plus 45, right, and 225 is one straight line. And negative 45 and 135 is another straight line. So one of these poles go this way and another pole goes that way in the same line, right? Same line. And other 2 poles, one goes this way, the other goes that way. That is the asymptotes. Now these asymptotes intersect at one point, right, on the real axis, because you know the poles and zeros, right, the root locus rather is symmetric around the real axis. So what you have below the real axis, when you flip it over, you get the image on the positive or above the real axis. Because as you see, the when you see get the poles, if you get, let's say, pair of conjugate complex poles, they always come as pairs of conjugate poles, right? So now we need to find these four asymptotes, in fact, two straight lines. Okay, they intersect at some point on the real axis. So we want to find out that point. So there's an equation for that, asymptote intersection point here, alpha. The answer is you add all the poles, again, open loop poles, okay? Start points. Don't worry about uh, the value of the poles as you increase k, because they move all over the place. So this is basically open loop poles and open loop zeros. So add open loop poles, deduct the summation of open loop zeros, and divide by n minus m. So we have these poles, one pole at 0, another pole at -3, so 0 plus -3. One pole is over here, this is -3 plus j root 11 plus the last one -3 minus j root 11. So add them together, divide by n minus m. So n is 4, m is 0, 4 minus 0 is 4. The answer is 2.25 minus. So we can mark that point over here on the real axis, 2.25 minus. And this is where the two straight lines or four asymptotes intersect each other. Right. So now we gradually, this is like completing a painting, right? You draw the lines, arcs, points, and gradually you now getting to completing this root locus, right? Actually, I forgot one thing. It's pretty straightforward. Right over here, I just forgot one thing. When you draw the poles and zeros, right, on the axis, you can see these poles, four poles, and there are no zeros. So, right, altogether four poles. We actually can figure out parts of the root locus, right, on the real axis. If there's any part of the root locus on the real axis, we can figure that out. Can somebody tell me how we do that? We know that this part, the root locus, is on the real axis from here to here. Can somebody tell me how do we know that? This dark line from here to here is root locus, part of the root locus. How do we know?
So the first rule, sir?
From the
first rule.
Yeah, so explain that rule.
It says that the root locus is on the real axis
Yes.
to the left of an odd number of poles or zero.
Yes, exactly. So if I follow the real axis, if I'm here, I'm not to the left of an odd number of poles or zeros. In fact, I'm not on the left of any poles or zeros, right? Not to mention about odd. So therefore, this is not part of root locus. Root locus can be up or below, above or below the real axis, but not on the real axis, right? Up to this point. And then when I cross over to the negative side, I am to the left of one pole. One is an odd number. So I'm to the left of an odd number of poles or zeros together, right? Here we don't have zeros, it's all poles. So one pole is an odd number. So therefore, the real axis from here to here satisfy the first rule condition, right? Being to the left of an odd number of poles or zeros, meaning you satisfy the root locus condition. So part of the root locus is on the real axis from here to here. So when I pass this point, -3, I am to the left of 4 poles and zeros. 4 is not an odd number, it's an even number. So therefore, the real axis, right, any point beyond this -3 and to the negative side does not satisfy the root locus condition. Therefore, root locus cannot be on the real axis. So now we figure out this part. So if you look at this pole, this is when k equals 0. This pole, when k equals 0, these two poles, their positions at k equals 0. Now you know that when you increase k, this pole will have to start motion this way, not that way. And this pole will have to move this way, not any other way. Because we know this part is on the, this is root locus from here to here. So when you identify a part of the root locus, right, real axis or anywhere, you know that this is the path the poles take when you increase k from 0. But the thing is, now these two poles, they meet up at some point. And what will happen after that? Right? What will happen after that? And when you increase k, what will happen to these two poles? Now you know that all these poles will have to go to infinity. So therefore we can say this pole and this pole, they will go to infinity like that. These two poles will meet up somewhere here, and after that they will go to infinity like this. So you can imagine now what is likely to happen here. So this is asymptote intersection point. Asymptote intersection point. The two asymptotes, four asymptotes, so two straight lines, they meet up over here. But this is not the point where the two poles meet up each other. This pole and this pole, they meet at some other point. Okay. Right. So let me take the breakaway point first and this one later. Okay. So focus here, breakaway point. So breakaway point means now these two poles, they meet up at some point and then they split. So we won't figure out the meeting point on this axis, right, between here and here. So for that, we use this equation, breakaway point. You get 1 over HSGS, right? 1 over HSGS, and differentiate with respect to S and set it to 0. This is to calculate the breakaway point. Now here HS is 1. GS is 1 over this whole thing. So when you have 1 over GS, you get the numerator, denominator swap each other. Numerator goes to denominator, denominator goes to numerator. So the numerator is 1 for the GS. So therefore, it will stay here as the numerator. Actual denominator goes to the numerator here. So it will become like this. Just the denominator of GS differentiated with respect to S set to 0. So when you do that, you can follow the mathematics. It becomes like this: 4s to the 3 plus 27s to the 2 plus 76s plus 60 is equal to 0. the solutions of this equation, third order polynomial, is the breakaway point. Now, there are ways to figure it out, right? But I'm going to tell you one of the most classical methods, numerical methods to calculate the solution of this equation, right? That is using a Newton-Raphson method. Before we get going with Newton-Raphson, right? Now, if you set this as your fs, this function as your fs, substitute for s -2, just a random number, right? -2. The answer is less than 0. It's a negative number. And then substitute for this one -1 for s, right? Then s to the 3 means -1. S to the 2 is +1. S is -1, like that. Then it becomes a positive number. Now you can see this one. When you select s -2, the answer is negative. When you select s -1, -1, the answer is greater than 0, positive. So therefore, the answer becomes 0 in between these two numbers for s. So the solution has to be between -2 and -1. So let's assume an initial answer, initial guess, say in between these two numbers, which is -1.5. Right. So I'm going to teach you, show you Newton-Raphson method also here, right, while we are making a headway. So we know pretty sure that now this equation, which is equal to 0, right? The answer should be between -2 and -1. So the initial guess is -1.5. Now, what is Newton-Raphson method? You have done this at some point in engineering mathematics. This is a function of x, fx. This is x, fx. So let's say it's like concave function like this, right? And if you pick up a point on the axis, on the curve, let's say fx0, right? And make a tangent here, that point, tangent, and it crosses x-axis at that point. Let's say this is x1, right? And this is the tangent of the function at this point. Let's say this is x0, right? You can write down this equation that fx0, this height is equal to this base length times tan theta. The base length is x0 minus x1. This is the base times tan theta. What is tan theta? It is the first derivative, f dash x, right? Evaluated at this point, x0, right? You have to calculate the increment, interception and increment, right? So the tangent here is basically f dash x at x equals x0. So we call it f dash x0. Because you know the function fx, you can calculate f dash x. You just have to differentiate, okay? So you know both functions, fx and f dash x. Then you can substitute any value and evaluate the function and evaluate the tangent, the gradient, okay? Now, when you put these into these equations, the function value, the gradient value, right, and also the value as x0, you can calculate x1. Very easy. So when we rearrange this equation, x1 is equal to x0 minus fx0 over f dash x0. So this is the equation we use to calculate x1 from x0. After that, we use the same equation and put x1 and calculate x2. After that, we use the same equation, substitute x2 and calculate x3. So this is always the next value. So when you proceed like this, starting from x0, let's say, right, you calculate x1. Now you do the same equation at x1, and then this is the tangent. You calculate this value. You do this again and again and again, and what happens is that you get from x0 to x1, x1 to x2 over here, x2 to x3, like that, eventually to x star, which is actually the point of intersection on the x-axis, right? So this is just a revision of Newton-Raphson method. Now here what we have is this function. This is our fs. So you need to differentiate this with respect to s to get f dash s, right? Because we need both. So when you differentiate this with respect to s, it becomes 12s to the 2 plus 54 is s plus 76. So use the function and its derivative, and the start point S0 is minus 1.5, and then calculate S1, the next point, right? And you can do the iterative process until you converge to the actual solution of the function. So this is how it works. Initial value is minus 1.5. We substitute for S0 and want to calculate S1. This is the equation fs0 over f dash s0. So this is fs0. This is f dash. Once you differentiate this one, right, you get this one like 12s square plus 54s plus 76. So evaluate this at s equals s0, right, which is minus 1.5. So substitute for s, get the answer, and it will be minus 1.19. So you started from 1.5 minus, right? And the new value is minus 1.19. Now you do it again. So use this one, 1.19 negative as S1, right? And calculate S2. So when you do that, for Fs, you calculate, you substitute minus 1.19. And you do the same for F dash S over here, 1.19 minus. Then you get minus 1.23. So like that, you can continue couple of cycles, then you converge to a value which is now not changing anymore. So when the change is negligible, you stop the iteration, and whatever remaining with is the solution. So for this one, we stop there for the iterative process, and we'll say it is minus 1.23 is the breakaway point. So which means these two poles, they meet up at some point, minus 1.23. And that is the point where these two poles meet up each other, and after that, it will split. One goes up, the other one goes down. So now we can safely say this one which is going upwards will align with this asymptote. The one which is going below, right, will use this asymptote to reach infinity. So it has to, it is logical to imagine it that way. Now let me take angle of departure. I think we skipped for a moment. Angle of departure. Now, if you look at these poles, right, we know that these two poles, they are moving on the real axis. and they meet up somewhere here, right, at minus 1.23. After that, they split and one goes up, the other one goes down. What about these two poles, this one and this one? So when I start increasing K, what is the heading direction of this pole? Whether it goes up, down, left, right, or any other direction. So that is what is called angle of departure. So you have to calculate angle of departure for one of these poles. Then the other one would be the mirror image. How do we calculate that angle of departure? I think we have the equation, this one. What you see here is the method that we use to calculate angle of departure, right? Do you remember this graphics? There's a pole here, and this theta 1 is the angle of departure, right? You get all of the zeros minus all of the poles, the angles, and equals to plus or minus 180 degrees. Now in this open loop transfer function, we don't have zeros, so therefore this is not there, this part. Only the poles. Only the poles. Now take these brackets one by one and substitute to it this particular pole. This particular pole. And calculate the angles. So when you substitute the value of the pole, right, to the bracket where the pole is the same pole, right? This is the angle of departure. And we don't do anything there. We just write as theta I, and all the other angles are known. Then you can actually calculate this angle of departure. So that is the technique. Right. So we selected the this pole minus 3 plus j root 11. We want to calculate the departure angle for this pole. Departure angle for this pole. So what we do is we get the first term of the transfer function, open loop transfer function. Let me show it to you again. Oops. Right. There's nothing here in the numerator, but there are 1, 2, 3, 4 poles in the solutions in the denominator. So we have to take one by one. So this term here, S is actually S minus 0 bracket. This is plus 3 bracket. This you can write down as 2 brackets, right? One is the positive, the pole with the positive imaginary quantity, and the other one is with the negative imaginary quantity. So you can write 4 poles. So the first one with 0, right? It is the S minus 0. Now what is S? Minus 3 plus j root 11. So you write it like that. S minus 0. This is the first term. This is the first term. So watch very carefully, right? The first term is this one, S minus 0. So in place of S, you substitute the value of the pole. So it becomes like this, minus 3 plus j root 11 minus 0. The second one is S plus 3. So for that, you substitute S plus 3. So this is there. This is S. minus 3 plus j root 11. The pole, you want to calculate the departure angle of, you write it over here. Okay, plus 3 is anyway there. Then the third one is the departure angle, because you want to calculate the departure angle for that particular pole, minus 3 plus j root 11. So we write it as theta minus the other one, minus 3 plus j root 11 minus 3 minus j root 11. This is the fourth term of the transfer function. So now you have to calculate the angles of each term. And if you go to the first one over here, minus 3 plus j root 11, you can sketch it on paper. Minus 3, the real part, plus j root 11. That is a positive imaginary quantity. Then the angle is 180 degrees minus tan inverse root 3 over 3. Okay, so I can just draw it over here and show it to you. So if I draw a line like this, minus 3 is over here. This is minus 3. Then over here, minus j root 11. Point is somewhere over here. So the angle is this one. Okay, but we write it as the other angle, right? This angle, which is 180 minus this angle, right? So that is tan inverse root 11 over 3. So then you get this angle. Then if you look at this one, the second one, minus 3 plus 3 cancel out. So it is j root 11. So j root 11, you have something like this. So angle is 90 degrees. Okay, so that is why 90 is here. Third one, theta, the angle we want to calculate. The fourth one is again 90, but it is so see it is this one, minus 3 plus j root 11 minus 3 plus j root 11. So this 3 cancel out. It will be plus j root 11 plus j root 11. Okay, so it is 90 degrees negative. So if you follow through, you will see this is 48 degrees minus theta, right? Then on the right hand side, 2k plus 1, you can remove that one. Get the without any revolutions around the origin. So then theta is minus 132. Okay, so this can be a bit confusing if you do not concentrate fully, right, onto what is happening. So theta is minus 132. So minus 132 is something like this way. So it probably goes like that, right? And on the other hand, the other conjugate pole will go like that. These two poles meet up over here, then one goes this way, the other one goes that way. So now it is a bit more clear for us the shape of the root locus. Next up is if you want to calculate the gain at the breakaway point. So as you know, you can calculate gain at any point, right? What is the value of gain which will bring the poles to this particular location, that location? So when you have 4 poles, you don't have to specify the locations of all of these poles, right? Just one of them. If you know you want to have one of these poles located there on the root locus, get the root locus point and substitute it to this equation. Remember, I will pedal back and show you that this one, gain calculation. The gain, right, for a particular point on the root locus is given by 1 over HSGS when S is equal to that point. So you have 2 poles on the real axis, the moving heading, and if you want to calculate, okay, what is the gain which brings these 2 poles on top of each other, right? You have to find out that point and then substitute that point to this equation. You get the gain for that. And HS is equal to 1. So therefore, this is 1 over GS. When you say 1 over GS, it's easier to write it as this way. Denominator over numerator of the open loop transfer function GS. So now we have only a denominator. The numerator is 1, right? So denominator, this part comes over here, only that part. So you have to write down that part and substitute for S. The value of S is actually the breakaway point. So when they meet up at that point, calculate that value, right? We got that point using Newton-Raphson, that is minus 1.23 something. Substitute that to this equation, right? Numerator is 1, is basically the denominator. Okay, so magnitude of denominator is the answer when S equals 1.23 negative, right? So this is minus 1.23 minus 1.23 plus 3. This is the pair of conjugate poles. Get the entire magnitude, right? That is 30.77. Let's say 30.8, right? So 30.8, let's say 31, right? Is the gain which brings the 2 poles on top of each other at this point. So this will be a specific case. It has some specific characteristics in the response. If you want to achieve that behavior, you have to set your gain to 31. Okay, so when you set your gain to 31 over here, you get that performance. We have 2 real poles on top of each other. Other 2 poles are anyway oscillatory, right? Because they are, one is up, the other one is below the real axis, right? They are oscillatory poles. Now, we have come to the final stage. These 2 poles, when they meet up over here, one goes up, the other one goes down. So at some point of time, as they reach infinity along this asymptote, at some point they're going to cross over to the positive half plane. And that is where system becomes unstable. Okay. So how to calculate the maximum stable gain of the plant? So for that, there is a um, um, simple technique using the polynomial coefficients, right? Developed a long time ago. So this is basically looking at the numbers, the polynomial characteristics, right? When the system becomes unstable, you can figure out that behavior if you follow this simple number game, right? Using the coefficients of the characteristic equation. So the characteristic equation is the denominator polynomial set to 0, right? That is s times s plus 3 times s square plus 6s plus 20 plus k, right? So this one you set to 0. This is the characteristic equation of the closed loop transfer function. Closed loop transfer function, okay? So that is why k is there. Otherwise, k is not there. If it is open loop transfer function, we don't say particularly a characteristic equation. So when it is closed loop only, we say that. And k is always there in the characteristic equation of the closed loop system, right? So when you expand this, you get s square, s to the 4 plus 9s to the 3 plus 38s square plus 60s plus k equals to 0. Now, follow very carefully this technique. There, what you do is you prepare an array, right? First column, second column, third column, and so on. So what you do is you get the coefficients of the polynomial, that is 1, 9, 38, 60, and k. And you write it in this order: 1, 9, 38, 60, and k. Okay, in this pattern: 1, 9, 38, 60, k, and 0. And then what you do is you go to the third row. You want to fill the third row of the array, right? When you fill the third row, what you do is you get the previous rows: 9 times 38 minus 1 times 60. 9 times 38 minus 1 times 6 divided by 9. The answer is 31.3. Then you do the same for the next column. The value here is 60 times k minus 38 times 0 divided by 60. The answer is k. Then you go to the next row here. So 31.3 times 60 minus 9 times k divided by 31.3. The answer is 60 minus 0.29 k. So you can continue that. Now, the stability of the plant is maintained, right, as long as the first column here, these coefficients are all positive. So we know that 1 is positive, 9 is positive, 31.3 is positive. This one we don't know. 60 minus 0.29 k. If this is positive, or as long as this is positive, system is stable. The moment this becomes negative, system is unstable. So therefore, you have to check this 60 minus 0.29 k, right? It has to be greater than or equal to 0, which means k should be less than 208. So it's a very simple array, right? Truth array. You put the numbers in and get to the first expression, which is appearing on the first column, right? With some inequality, right? It can be 0, or it can be positive, or it can be negative based on the value you select for k. So when you reach that level, right, write down the inequality for stability and calculate the inequality for the gain k. And in this particular case, it is 208. So if you set the value 208, system is about to be unstable. Now we spend a lot of time trying to visualize the root locus of this plant. But if you go to Matlab, it is few seconds. It is few seconds. So you have to do a complete root locus design yourself. I'll give you a couple of examples, right? I'll send you an assignment, the first one. You can work it out on root locus. But if you know it, how it works, you don't have to keep doing it. Instead, you can go to Matlab and follow a few steps. You will see the root locus on your screen. For this particular example, it is only some 5-6 lines, as you can see over here. You first introduce your plant, open loop plant. How do you do that? The open loop plant is 1 over s times s plus 3 times s square plus whatever, right? Second order term. So this is how you write in Matlab. Numerator is 1. Denominator is this 1 0 means s plus 0 meaning s, and then this 1 3 bracket means s plus 3. This means s square plus 6s plus 20. So this is the order, the format Matlab uses to declare polynomials. If you say 1 6 20, it is actually s square plus 6s plus 20. If you say 1 3, it is s plus 3. Okay, so this convolution means actually multiplication. You multiply these two together and the result you multiply with s plus 0, which is s. So numerator is 1 within bracket 1. If you just write 1, it's not a vector anymore, right? So denominator is written like this. Then transfer function is numerator over denominator. So you create the transfer function. You create the open loop transfer function. Then in Matlab, R locus G, just one word, it will generate the root locus on your screen like this. Now, if you look at this one, you see the same thing we were sketching, taking a lot of time, right? You can see the open loop poles, right? One is over here, the other one is over here, other two are there. So we figured out this point from here to here on the root locus on the real axis is actually part of the root locus. Fine, it is there. You can see the green and blue and the red, these are different poles, right? So these two poles move each other head on and meet up at this point, that is minus 1.3 or something, and after they split, one goes here, the other one goes there. Now I follow my mouse and put it over here and click, right? Then it will tell me the value of the gain here, among the other things. So when I bring the mouse to any point and click it there, you will see the gain is 208. See, our manual calculation also 208. Okay. And the conjugate pair, they have the angle of departure minus 132. Remember? So this is minus 132. Goes like that. The other one goes like that. Perfect. So if you want to calculate your gain for anything, right, any other point, just take the point from the screen, right here or here, can be anywhere. And you can put it to that equation and calculate the gain, which is the gain which will bring the pole to that point. Right. Now that concludes the root locus design part. Now, how do we use this technique to design a feedback loop? In fact, to calculate gain, you just need to figure out where you need to place your poles. Right? Here, 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 or any point. Once you figure that out, you can go to the internet, to the Matlab and figure that out. It will tell you the gain. What it does is, it uses this equation and calculates the gain for you.
Excuse me, sir.
Yes, go ahead.
I have a small question.
Yes,
At the
yes.
breakaway point,
Yeah.
what decides which pole goes in which direction?
It doesn't matter. You don't need to know. Nobody knows. Doesn't matter. Because there are no now let's say the pole which is coming from here to here, right? The pole coming from here to here. I don't really mind whether this pole goes this way or this pole goes that way. There's no identity after that once you have both poles here. So even though we say poles are moving, right? It's actually not poles are moving. They are jumping, right? When you set your K, they're jumping from one point to another. There's, in a way you can say, so it's like different picture movie. When you flip them faster, you see the motion. This is something like that. This motion can be taken away. So when we take that motion thing away, there's no problem, right? So it's actually a good point, but it awakens minds of what is actually happening. For a specific K, there are positions. That's it. Don't have to worry about moving poles from one to the other. For teaching purposes and ease of understanding, we teach it like that. Is that clear?
Yes, sir.
So in Matlab also it draws like that, green goes like that. So you tend to believe that this particular pole is going like that. There's no such particular pole kind of thing. For whatever gain, there are solutions. For different gain, there are different solutions. These solutions, they are not the same. They're not connected in any way. Okay. Any other questions, please? Okay, then let's take a little break.